Hello, we're going to look at a couple of application problems involving exponential functions and derivatives. So here we have a population model. Population in millions of a particular city is given by the function p of t equals 39.94 times 1.012 raised to the t, where t is years after 2000. So what was the population in 2010? So t is years after 2000, so 2010 is going to mean t equals 10. So here we're just looking for the population, no change. So we're just going to plug in t equals 10. And when we plug that into the calculator, we get 49.17. And then our units are in millions here. What was the instantaneous rate of change in the year 2010? So instantaneous rate of change, remember that's another word or another phrase that means take the derivative. So we need to take the derivative of our function. So this 39.94 is just a coefficient, and then the derivative of 1.012 to the t is going to be 1.012 to the t times the natural log of that base. And then if we wanted to find the instantaneous rate of change in the year 2010, we are going to just plug in 10 into that equation. And that value is 1.02. Our units on this are going to be millions, just like our population, but since we're taking this with respect to this derivative with respect to time, it's going to be divided by our unit on time. So we're going to get, that means that this population in the year 2010 was growing at about a rate just slightly more than 1 million people per year. Suppose a person is going up in a hot air balloon. The air temperature decreases with height in feet according to the function t of h equals 71 times e to the negative 0.000065h. How fast is the temperature decreasing at a height of 1,050 feet and at a vertical speed of 800 feet per hour? All right, so how fast? That typically means that we need some kind of length. In this case, feet is our length unit, divided by some kind of time unit. Feet per hour would be our vertical speed. Our function here is giving us air temperature. So the units on this are going to be in degrees. So if we want to find how fast it's decreasing, that is a rate of change. So again, that means take the derivative. So if we find the derivative of our t function, we get 71 times e to the negative 0.000065h times the derivative of that exponent, which is negative 0.000065. And let's go ahead and pull the calculator out on this one. So we have 71 times negative 0.000065 gives us a coefficient of negative 0.004615. We still have it multiplied by that exponential. Now we want this to be at a height of 1,050 feet, and that's going to give us our temperature change as far as how far we've gone up if we multiply that or plug in that h as 1,050. So in our calculator, that's our coefficient times the exponential function e to the negative 0.000065 times our h value of 1050. And so we get 0.0043 approximately. And the units on this are in temperature, which is in degrees, per our height is in feet. So this is in degrees per foot, or degrees per foot. We want to know how fast is the temperature. Oh, I made a mistake up here. We want to know how fast is the temperature decreasing. And so that is going to be in degrees per hour. How fast typically means we want a time unit in the bottom. Well, we've got a length unit in the bottom. That's not going to be how fast, but we know that we're going up at a rate of 800 feet per hour. So we can just multiply this by 800 feet per hour, and those feet units are going to divide out, and we'll be left with units of degrees per hour. So let's take that answer that we have in the calculator and multiply it by 800 feet per hour, and we get negative 3.45. And the units on that are degrees per hour. So decreasing is correct because we do get a negative number here, and it's decreasing at a rate of 3.45 degrees per hour. All right, I'll see you guys next time.